In this video, I'm going to show you how to do the calculations for an enthalpy of combustion investigation. So in the investigation, you've combusted an alcohol in a spirit burner and you've tried to capture that heat in water in a container. And we're going to work out the enthalpy of combustion of the alcohol. To do that, we need to know the total amount of heat that was released when it combusted. So that's the heat that was absorbed by the water and the container. And we need to know the amount of the alcohol that was combusted. So we're going to work out those two things separately. First of all, we need to work out the amount of heat that was released when it combusted. And that heat was captured by the water in the can. So we need to work out how much heat did it take to increase the temperature of the water by however much it increased, and how much heat to increase the temperature of the can, and we'll add those two values together for the can and the water. Let's do them separately. So first of all, to find the heat absorbed by the water. Okay, there's different ways to lay out your working, but I find it helpful to put little subheadings showing exactly what I'm doing. Now the formula we're going to use is Q equals mc delta T. So for calorimetry, that's always going to be the equation that you will be using. And we're going to list our data. So I'm going to list the data down here and put my working over here. Let's assume that the mass of the water was 150 grams. My specific heat, I'm going to leave a space, you'll see why in a second. The specific heat of water is, from your formula sheet, 4.18 times 10 to the 3 joules per kilogram per Kelvin. Now you'll notice that the specific heat is in kilograms per kilogram. So I'm going to convert my mass of water to kilograms, and whenever you're doing a calorimetry question, or whenever you're using the specific heat, convert it to kilograms, because that way you won't make any mistakes with units. So my mass is 150 grams, that's 0.150 kilograms. And I need to know the change in temperature. Well, in this investigation, let's imagine that the change in temperature was 22.8 degrees Celsius. That's how much the temperature of the water increased. This is in Celsius and this is in Kelvin. Celsius and Kelvin are different, but when you're measuring a change in temperature, it doesn't make any difference whether it's in Celsius or Kelvin. For example, if water is 0 degrees Celsius and it increases to 1 degree Celsius, the change is 1 degree Celsius. If I convert to Kelvin, it went from 273.15 to 274.15 Kelvin, it still increased by 1. So when it's a change in temperature, Celsius and Kelvin are the same. But if I want to show my understanding, I could put that it's the same, 22.8 Kelvin, to show I understand the units here. Now I'm going to substitute these values in. So what do I get? Mass, 0.150 times C, 4.18 times 10 to the 3 times T, 22.8. I plug all that into my calculator and I get 1.430 times 10 to the 4 joules. And for enthalpy, we're always going to end up working in kilojoules, so I'm going to straight away convert that into kilojoules. 14.30 kilojoules. You'll notice that I've kept 4 significant figures in my data. I've got 3, 3, 3. So 3 significant figures in my final answer, but in my working, I keep 4 significant figures until the final answer, when I'm going to drop it back to 3 significant figures. One other quick thing, how did I get from joules to Kelvin? If you struggle to know whether to multiply or divide, you can write definitions. For example, if 1 kilometre is 1,000 metres, that tells you how to convert from one to the other. If I have kilometres and I want to get to metres, what do? How do I get from 1 to 1,000? I multiply by 1,000. So if I have kilometres, I multiply by 1,000 to get to metres. If I have metres, how do I get to kilometres? It's really clear I need to divide by 1,000. Exactly the same, if you write the definition of a kilojoule, that shows you very quickly how to convert from one to the other. If I have 1 kilojoule, how do I get to joules? I multiply by 1,000. If I have 1,000 joules, I divide by 1,000 to get kilojoules. So my answer up here, 1.430 times 10 to the 4, how do I convert that to kilojoules? Clearly I divide by 1,000, and that's what I've done. If you type that into your calculator and divide by 1,000, you'll get that. So this is the heat absorbed by the water. Now we do exactly the same thing to find the heat absorbed by the can. So the heat absorbed by the can, it's going to be exactly the same. Now it's going to be the mass of the can. It is a good habit to make sure this is clear. I've got M twice. This time it's the water, this time it's the can. I've shown that by having a heading, but you can do things like this. It's very helpful to put in brackets what it's the units, what I'm actually giving the value for. So in this case, I could put M can if I wanted to avoid any confusion. Okay, in this example, let's imagine the mass of the can is 14.2 grams. The specific heat, what's it going to be the specific heat of? The can was made of aluminium, so I do a little bit of research. I find the specific heat for aluminium, and let's say my value I found said 0.902 times 10 to the 3 joules per kilogram per Kelvin. Again, I'm going to convert this to kilograms, so 0.142 kilograms. So I've got my mass in kilograms, my specific heat. My change in temperature is exactly the same because the can heated up by exactly the same amount as the water. And so I do exactly the same thing. Q equals MC delta T. I'll plug those in. 0.0142 times 0.902 times 10 to the 3 times 22.8. I plug all that into my calculator and I get 292.0 joules. And again, converting it to kilojoules, I get 0.2920 kilojoules. And again, notice that I've kept 4 significant figures. This 0 here before the decimal point or at the start of a number is not significant. I've got 4 significant figures. I keep 4 because that's 1 more than what I've got in my least number of significant figures in the data. This has got 3, 3, 3. So I'm going to keep 4 because it's only a working out step. So what's the total heat absorbed? Total heat absorbed, or that's actually the total heat released in the combustion. So total heat released by the ethanol when it combusted is equal to, it's going to be this value, the amount of heat absorbed by the water, plus the amount absorbed by the can, because that's the total heat that was released. So it's going to be 14.30 plus 0.2920. So I've just add together the heat that came out of the ethanol and was absorbed by the water, plus the heat that came out of the water and was absorbed by the can. What was the total heat that came out of the ethanol and was absorbed by the can and the water? When I add them together, I get 14.59 kilojoules. And I've kept 4 significant figures. Now, that's the first part. I've worked out the total amount of heat that was released by my ethanol when it combusted. The second thing I want to do is work out how much ethanol actually combusted. I need to know the number of moles of ethanol. So how do we do that? Again, I like to put little headings to show what I'm doing. To find, you could put the amount of ethanol. I'm going to put moles of ethanol, just so that I don't get confused and I know exactly what I'm doing. What do I need to know to do that? I need to know the mass of ethanol. I need to know the molar mass of ethanol. And then I'm going to use number of moles is mass over molar mass. You'll know the value for your mass of ethanol. Let's say in mine that 1.83 grams of ethanol was used. And molar mass of ethanol, well, I'll just write over here so you can see CH3, CH2OH is ethanol. So what's my molar mass going to be? It's going to be 2 carbons, so 2 times 12.01 plus 6 hydrogens, 6 times 1.008 plus 1 oxygen, 12.01. Sorry, 16. So plus 16. Thinking of carbon, I was moving ahead in my brain to the next step. So we add all them together, we get 46.068 grams per mole. Molar mass is always going to be grams per mole. If we had 1 mole of ethanol, what would the mass be? 46.068 grams. So we've got a molar mass. And so if I know the mass of ethanol I had and the molar mass, I can easily work out. It's good not to have your working quite so spaced out. I normally write all my data first, then I write the formula, but I wrote the formula first so you could see what I was going to do. So what do I get? 1.83 divided by 46.068. And when I plug that into the calculator, I get 0.03972 moles. And again, I've kept 4 significant figures, one more than I had in the original data. So I know that this is the number of moles of ethanol that combusted, and I know that when that many moles of ethanol combusts, it released this much energy in kilojoules. So I can easily work out, if I had combusted 1 mole of ethanol, how much energy I would have got. How do we do that? Just a little trick if you struggle to work out which one to divide. In the end, the units we're going to have are kilojoules per mole. That's what we're trying to work out. How many kilojoules do I get per mole? Well, kilojoules per mole just means kilojoules divided by moles. That tells you the equation to use, how to calculate it. If you want to know kilojoules per mole, you take your answer in kilojoules, you divide it by the answer you've got in moles. Kilojoules divided by moles will give you the answer. So I know that I need to take this answer, the amount of energy that was released in kilojoules, divide it by the number of moles of my substance, and I will get an answer in kilojoules per mole. How much energy do I get released per kilojoule, per mole of ethanol that combusts? Now, that would give me the heat of combustion of ethanol. But we're actually after the enthalpy of combustion, and it is slightly different. What's the difference? How do these two relate? When I combust my ethanol, energy is released. That's my heat of combustion. The ethanol is losing energy because it's being released. So when there's a positive amount of energy released as heat, the amount of energy stored up in the ethanol is actually dropping. It's losing its energy. And enthalpy is sort of like the total energy stored up in the substance. So that's going to drop when it gives out energy. So that's why if the energy released is positive, the heat of combustion, the heat given out, I would expect my enthalpy change to be negative. The substance itself has actually lost energy. And so this is an exothermic reaction. It's given out energy. The enthalpy change is negative. Now, how do we work it out? So we know this is the amount of heat that was released. To work out the enthalpy change, we need to change the sign of that, because if heat is released to the surroundings, the heat given out, that's a positive amount of heat given out, the substance has lost enthalpy and the enthalpy change is negative. So the enthalpy change is negative the heat that was given out and divided by the number of moles. So it looks like this. If I want to work out the enthalpy change for the combustion, for the alcohol, it's the amount of heat that was given out, but I'm going to change the sign. So negative Q. Negative the amount of heat given out, divided by the number of moles of alcohol that burnt. And when I substitute in negative Q, so I've got minus 14.59 divided by the number of moles, 0.03972. And when I work out that sum, I get 367, minus 367 kilojoules per mole. Again, I've got to put units. Make sure you put units on every answer. So it's how many kilojoules of energy did the substance lose for each mole that was combusted? Minus 367. So it's an exothermic reaction. And now I've dropped my number of significant figures down to 3 because this is my final answer. And all the way through, the lowest number of significant figures I had in my original data was 3. So my final answer is 3 significant figures.